Good afternoon, everyone. We're going to go ahead and get started. I know some last-minute people are arriving to the webinar, but we'll go ahead and get started. First of all, thank you for attending today's webinar, which is a partnership between SCIA Engineer and SDS2 Design Data, Designing Steel Structures with SCIA Engineer and SDS2. My name is Ben Follett. I'm the U.S. Product and Marketing Manager for SCIA in the United States. With me today will be a friend and colleague of mine, Steve Ashton. Steve is the SDS2 engineering representative, and he'll be showing us a little bit about SDS2 a little later. And so before we get into the meat of our presentation, I want to just mention, for those of you that don't already know, SCIA and SDS2 are both part of the global software company, the Nemetschek Group. And so the Nemetschek Group is a group of 14 different brands, all practicing within the architecture, engineering, and construction space. And so in the United States, you may be familiar with us from our brands Graphisoft, which sells ArchiCAD, Vectorworks, obviously Bluebeam, and SDS2 are very, very familiar to you, as well as maybe Celibri, which is a competitor to Navisworks, and finally SCIA Engineer. And so a little bit about SCIA. SCIA Engineer is a company that works with many different large engineering firms across the country and across the world. These are some of our customers both here and in kind of mainland Europe, where we're very popular. So you can see that we do have a lot of large engineering companies, whether they're just in-house structural companies or large industrial firms that do some of their own structural or manufacturing work within the companies. In addition, SCIA Engineer is very kind of flexible, and so it can do a lot of different things for a lot of different types of projects, so it's really not limited to any one type of project. And so with people using SCIA Engineer, we find them working in the office and residential space, the industrial buildings, energy-related projects, whether it's towers or masts or support structures, infrastructure and bridges. Now, although that's not so common here in the United States, it's certainly common abroad. Environmental structures like tanks or pools. And then finally, just kind of this idea of these general structures, which we find or specialty structures, which can be scaffolding or really anything that doesn't quite fit into this kind of space. And so with that, I want to turn it over very briefly to Steve so that he can give you a little introduction to SDS2.
Right. I'll just tell you a little bit, give you a quick overview of what SDS2 is. We're headquartered in Lincoln, Nebraska. We have several different solutions available. One that is not shown up here on the screen is SDS2 Concrete. It's a fairly new one. The middle one, SDS2 Detailing, is our flagship product. It has intelligent connection design and detailing capabilities. SDS2 Drafting on the left and SDS2 Modeling to the right of that. They are both part of SDS2 Detailing. SDS2 Modeling is just in the 3D or the modeling part of the software, and the SDS2 Drafting is just in the 2D part of the software. Upper left-hand corner, SDS2 Approval is becoming more and more popular as engineers are realizing that it's much quicker and easier to approve a model than it is to approve shop drawings the old traditional way. And I tell you what, as soon as you do one job of approving a model instead of drawings, you'll never go back. SDS2 Engineering is mainly what I'll be showing today. That does have analysis capabilities, not as powerful as SCIA, but the main selling point is the connection design capabilities. SDS2 Connect works within Revit Structure, and which does connection design within Revit Structure. There's SDS2 Fabricating, which creates your CNC files, SDS2 Erector. We also have SDS2 Erector Plus Station, which has analysis capabilities, which allows you to take an SDS2 model and place a crane on the site, and you have hundreds of different options as far as cranes that you can place on the site and create erection plans. SDS2 BIM is for importing and exporting. Status or SDS2 Mobile, it works with your iPhone or Droid device. as far as scanning members as they're, let's say, arriving at the job site or as they're being erected, so you can create a color-coded model to see what's erected or what's delivered to the job site, or any status you want to picture. And then SDS2 Viewer is a free download that allows you to view SDS2 models. And SDS2 Concrete, which I briefly mentioned, that's a brand new product. You can model concrete footings, concrete walls, concrete columns, concrete beams, and detail the rebar and create rebar schedules, and also design embeds. So you can go to the next screen, Ben. Okay, and mainly what I'll be talking about today is the connection design capabilities of SDS2, and again, that's in SDS2 Connect, SDS2 Engineering, and SDS2 Detailing. One thing you'll see is SDS2 provides the largest variety of connections of any other software that does connection design. More member types, configurations, skewed connections, sloped connections, skewed bracing connections, and so forth. It has the most codes available of any other software that does connection design, including AISC, the Canadian code, the European code, Australian code, and so forth. You'll see examples of complete detailed calculation reports. One of the things also I usually stress is SDS2 does connection design versus connection verification, which means you put in the criteria ahead of time. You tell it, what size bolts you want to choose from, what plate thicknesses you want to choose from, what types of connections you want in what situations. Then you import the loads or put in the loads, and it will run through the iterations for you to design the connections. It takes into account not only the connection itself, but other connections framing into the same joint and other nearby connections, and runs the constructability checks, and I'll show an example or two of that shortly. And the connections are fully customizable. You can create any connection you want. So that's a quick overview, and you'll see that as part of the demonstration. You can take over, Ben.
Yeah, thanks, Steve. And so really today we're going to be talking a lot not only about the different internal functionalities of both SCIA, where it's kind of focused on modeling and analysis and steel design for an overall 3D structure, and SDS2 we're going to be talking about connection design, but also how the two interact together and how the exchange of information directly from SCIA Engineer to SDS2 can really help kind of grow the interoperability, grow the exchange, kind of this open flow of information between the engineer and the fabricator or detailer or erector. And so really what we see is that there's a lot of time savings that's currently happening. A lot of people are participating in BIM and interoperability on the front end of the project with the architects through Revit mostly, but really there's a lot and maybe even more time savings to be found doing the same type of exchange on the back end with the fabrication models. And so that's really what we want to show. And so without further ado, I'm going to go ahead and jump actually right into SCIA Engineer. And so for many of you, SCIA may not be a new product. You may have attended some of our webinars before and seen some of the information that we've provided, but this particular model, we're not going to build anything from scratch. We're going to just use this model and then kind of do some different things with it. But we've kind of got this basic structure that will eventually be transferred directly into SDS2 via IFC and some other additional information via XML. This particular model, you can see we've got a series of different steel columns, and so the steel columns are going to be designed obviously for the particular loads in SCIA Engineer. We've got some roof beams, some different kind of horizontal kind of skewed beams so that we can see both design and also how those connections then would be detailed in SDS2. We do have composite beams on the floor, so we'll look at some composite beam design. We also just have some generic roof beams here as well. We have different composite floors and roof decking as well, some horizontal bracing members, some vertical bracing members. And then we don't have it in this particular model, but we do also support the exchange of joists. So just no joists in this particular model for this particular example. Now, prior to running the analysis here, we obviously need to create loads, load cases, load combinations. And so in this particular case, if we choose load cases, we do have a few load cases already created. The self-weight's automatically created from scratch. We do have dead load, live load, roof live load, and snow load automatically created as well. And so if we look at a few of these loads, we can see, for instance, some of the surface loads that have been added for the snow load case right here. So we have some surface loads. We can look down and see maybe some live loading on the floor. And obviously these loads can be whatever you want them to be. They can also be used as different types of loads. So mostly in this particular case we are using surface loads, but we have point loads, line loads, moments, point displacements. I think that if I look at a dead load here, one of the things that we did do is we did add a few really concentrated dead loads to the ends of beams so that we could see how that information gets properly transferred into SDS2 for connection design. And so we'll look, Steve will be able to show us a little bit more about that when we get into SDS2. Finally, for combinations, the combinations are created from scratch. The combinations are created automatically by SCIA Engineer. And so there wasn't anything we did to create these combinations. This is a standard when we do steel buildings that have composite floors in them. We create automatically these construction stage and final stage strength and serviceability combinations. You could obviously always create your own combinations, whether it be a envelope combination, a seismic combination, or even just your own standard linear combination. It's really up to you, but in this particular case, everything that we need has been automatically created by the software. So before we go ahead and look at the design elements, we can go ahead and run the analysis. So I'm just going to go ahead and very quickly run the design. And so this should just take a few seconds here. We'll run through the linear analysis. Now we obviously have the ability to do additional types of analysis, nonlinear analysis, dynamic analysis. We're not really going to focus on that today. We spent some time in a webinar a few months ago talking about different advanced analysis capabilities in the software, and if you're interested in that, just let me know and we can provide you the link to that webinar, which is posted on YouTube. But now that we have the now that we have the results available, in this main service tree here where we kind of run all of the functionality of SCIA, we can go ahead and open up the results service. So in the results service, we can go ahead and look at maybe a certain selection of members. So in this case, I'm going to go ahead and look at this grid line so that we can really kind of dive into this particular group of elements. And so here with these selected, we can go ahead and just view some different results. So the first one maybe we want to view is some internal forces on the member, choosing a combination and maybe the final stage combination and looking at maybe not the axial load but the shear forces, right? So we see the shear forces in these particular elements, right? Now we can see maximum and minimums that are given. Right now this is based on the global max min, but we could also change it to member to see all the maximum and minimums that are available. These are in each individual member. This is graphical, obviously, and so we could change the different graphical inputs, or we could also look at some table results and go ahead and get a similar table of the same type of results here that's available graphically. And at any time, if you want to use this or you need to use this information maybe in an Excel spreadsheet, or you're trying to send this to somebody else and you want to send it to Excel, we do within the table results have a one-button click export to Excel. So just click this and it'll automatically export that to Excel. We also have some more, a ton of other results. One I always like to show is the displacement results. So if we go ahead and choose maybe our final stage serviceability case, we can see the displacement on the 3D structure here. So obviously we've got this shorter member with maybe some more load on it on this side, and we've got some additional displacement. Again, obviously all of this stuff can be viewed in, again, the table results. So again, we can see the table results and look at that 3D displacement, the minimums and maximums. And so these are just different types of, whether in this particular case 1D member or even 2D member or support even results that are available to us. Now these results for the most part will be sent directly to SDS2 for use in connection design where applicable. So all the end reactions and end moments will be sent directly to SDS2 and can be populated into the connection design for SDS2 so that you don't have to go ahead and add any more loads on your own. So with this same selection, once the results, all that code independent information, once the results are evaluated, we can go ahead and look at steel design. And so this is really the first level of design, right? Obviously, all of this steel design is based on some basic setup. We can choose from a variety of different codes that are supported for the American standards. And so we can choose whatever we want to use. In this case, I'm still using the 2010 edition of the steel code. We can also set our buckling defaults for how the system will buckle, whether we have all weak, strong, torsional, lateral torsional axes that are used in buckling. Additionally, we can go ahead and look at a member and get some real specific information about its buckling. So in this particular case, we can see, in this particular member where we have strong and weak axis buckling systems. Now in this particular case, I've eliminated, kind of removed a buckling system in the middle just so that we can say, hey, I want this unbraced length to be this full length of this member, right? And you can kind of manipulate and modify those things on either a group basis, on a global basis, or even on a member-by-member basis in SCIA Engineer. Now when we're ready, when our buckling has been kind of set, we can go ahead and choose one of our ultimate limit state checks. So we're going to either check LRFD or ASD checks. Again, in this case, we'll set a combination. So we'll set our final stage combination. And then we'll go ahead and look at a brief output for all these members. And so for these selected members here, we have just kind of a brief unity check. Now, we don't really have a ton of load on this system, and we're kind of sticking with the members that we have, but we can see the unity checks that are given here. So we've got 22% is our highest unity check. We can go ahead and look at this in a preview. We'll just give us a simple table of those members. So table with the load case, the member, the cross-section that's being used, the material that's being used, and then the final unity check. Now, if we wanted to see this in more detail, we could go ahead and maybe select this particular member. So I'll switch my selection to all, or excuse me, to current, and we can go ahead and look at a detailed output. So this detailed output, again, is just step by step based on the 2010 code here, exactly what C is doing in order to do this. So giving you the classification for axial compression and flexure, telling you the loads which are at the worst case output right now, and then going through the different checks: buckling, torsional buckling, strong axis bending, weak axis bending, shear stress, combined stresses check. If there's any torsion in the member, the torsional check then gets kind of added and applied, and then we get down to our final unity check. And so this is for every single member, every single steel, hot rolled steel member, or you get the same kind of output except for the AISI code for cold form members. Additionally, all this information is available in the engineering report, so we won't talk a whole lot about the engineering report today, but SCIA does have an engineering report that's a fully standalone package. It's launched right from within SCIA Engineer, and it's dynamic, meaning that any change that happens in SCIA, that change is automatically reflected in that engineering report. So you can have both open at the same time, and you can be kind of fluidly making changes to your model and having those changes update into the engineering report, so you can keep your documentation really as current as possible. Okay, so now if we go ahead and close out, we talked about steel design. We also want to, I'm going to turn back on the rest of the model here, we also want to talk a little bit about composite design, because this is kind of the other aspect of elements that we're going to send with some information to SDS2. So I've got this composite design, this floor. I'm going to go ahead and click on the composite service and just really quickly look at the setup. And so in the composite setup here, there's just a variety of different options: automatic, how we want to generate the combinations automatically, how we doing a designer check, how we want to include, do we want to restrict the beam depth, what kind of design approach do we want to do, basically how do we use a percentage of composite action, what studs or shear connectors do we want to use, how do we want to take into account camber, do we want to design it, what are our deflection limits. All those different things can be set either for a member by member or can be set globally. Now once we're ready to run the design, we can go ahead to composite beam design and choose to run the design and see our unity checks for each individual member. So if we go ahead and just kind of launch the design here, we see those unity checks. And so we have the unity checks for each member. We can see some of the controlling unity checks. If we also want to go ahead and look at the actual label on this, we can see the number of studs that are being designed for these particular members, right? And so we have, if we were going to design camber, camber would also show up here. In this case, we've got some pretty short spans, so really no need for camber. Again, we can show a brief output in this particular case, but what I want to show and what people really like about SCIA Engineer for this particular type of functionality is the detailed output. And so if I select one of these internal members here and we go ahead and preview this, we can see the detailed output. So this is the detailed output of the composite beam design. We can see all the forces that are applicable to this member, information about the cross-section and the decking that we're using. And so we are specifying a specific Volcraft deck with a specific amount of concrete on the top. We get the loads, so here are the loads that are being applied and the moments that are being found at these different places, and then ultimately we get to the stud design, right? So we're designing uniform studs in this case. We're looking at different detailing provisions, so we can see this detailing provision and see if any of these are failing. And then finally we get into step-by-step each stage, construction, and final strength and serviceability for the check. So we can see the unity checks for strength and strength in the final stage. So we've got our unity check for strength in the final stage. Obviously our serviceability conditions, so our deflection limits, this is where camber would obviously be kind of initiated if we needed to. And then finally all the way down to where we see our final stage, kind of our summary of results with kind of everything that's passing and failing. And so again, all of this information is available to be used in the engineering report, or a lot of this information will be sent directly from the design, will be sent directly to SDS2. So the last thing that we need to do is, I'm going to go, before we leave this design service, we're going to store, there's an action button here to store design info for export. And this is essentially just to save the information in a table so that it can be properly sent to SDS2. So that's going to send the camber, the reactions, all of the stud information directly to SDS2. Now, when the design's finished like it is now, we're ready to export information to SDS2. We're going to do that export in two fashions. One, we're going to export the geometry via IFC, and two, we're going to export the data like the studs and camber and the reactions and all that stuff via XML. The first thing we need to do is we need to make sure the functionality structural model is enabled. That gives us additional design parameters in the member data for the structural model. So basically we can set up in different kind of viewing or geometry characteristics of members that are structural only, meaning that they don't have any impact on the analysis model. So in this case, we could change the eccentricity, the alignment, this kind of priority value. In this case, we're requiring all members have the same priority for the export to SDS2. And we can set all these things individually so they don't change the analysis model. Basically, they're just set up in a way that will be properly transported to SDS2. So really, you're not going to change or impact your structural model at all if you've done some things different in your analysis model than you want or you would find in your SDS2 model. Maybe some alignments or some eccentricities or something like that. So in this case then we're going to go ahead and just generate our structural model. Now with our structural model generated, we can choose File and Export, and we'll export an IFC file. And we can just choose to save it on our desktop here. And then we'll get our export options for IFC. And within our export options for IFC, we'll just choose units. And then we can really just, all the other options are standard. We can just choose kind of which elements we want to export in this case. So in this case, we're going to export 1 and 2D members and line grids. This is the information that's going to come to SDS2 via IFC. So we can just click OK. The export is complete. So now all the geometry has been sent then to an IFC file that can be imported into SDS2. Now the last part of this is exporting all of kind of the analysis data. And so if we go to Tools and XML, we can set up the export for an XML file. Now SCIA has created by default a stored kind of setup of the document of the way that data wants to be exported to SDS2 via XML. So these tables are already set up, they're already standards. Obviously you can change and manipulate them, but there's already a template set up for you. And so all this information, composite beam information, internal forces, supports, all that information can be sent as additional information to SDS2. So when we're ready again, we'll choose the export button. Again, just choose wherever we want it to be. We can just save it. And then once we're ready to go, we can click export, and we can export the model, or export, excuse me, the XML, that text file, so that it can be read into SDS2. So at this point, we have all the information defined such that we can now kind of make this transition to SDS2 for the final connection design and detailing. So it's this time I'm going to go ahead and switch the presenter to Steve so that he can show us the import and the connection design in SDS2.
Excellent. Now you can see my screen. Okay. So we got SDS2 opened up right now. I started a new project. It's blank. There's nothing in it. First thing we're going to do is bring in that IFC file that Ben created. So we do that by clicking Design link here, which is the importing function of SDS2. And then we browse to where that IFC file is, which I saved on my desktop here. Here it is. And I'm going to uncheck set main material to user. And what it shows here, it doesn't recognize the slabs that are coming in, so I'll say import this as miscellaneous, the 3 slabs. And then some minor adjustments were made, and then it tells me that it brought in the 11 columns, the 40 beams, 9 vertical braces, and 3 miscellaneous members. So next thing we'll do is open up the model. And one thing that's not brought in, or that doesn't exist in the SCIA model actually, that will add to the SDS2 model is column base plates. So we'll do that easily here by setting the selection filter to columns, grabbing all of the columns here, and then editing. And just to make things easier, we'll just add the same base plate to each column. And let's see, process here. And if you're wondering why we have such a small job, it's you really have to have a fairly small job when doing a 1-hour webinar in order to make the process time as short as possible. The next thing we need to do is, as you can see, the brace points are at the top of beams here, and what we're going to do is drop them to the half depth of the beams, and that's you can do that in one option here. Just going to Edit, Change Option, Set Vertical Brace Work Points to half nominal depth of supporting beam. Yes, we do want to do that. It tells us which members it did that for. And as you can see, now the brace work points are at the half nominal depth of the supporting beams. And let's see, one other thing. We have not imported that XML file yet. So if you look at these beams, right now the loads are set to auto instead of having the actual loads brought in, and I'll show you what that means shortly here. So the next thing we'll do is import the loads, and we do that by going to Model, and we have a parametric for that, parametric run, and then we go to our desktop and we run the parametric SCIA XML import, which finds the XML file that Ben sent over, and up here it shows it what it's doing. It's bringing in all of the connection loading information, bringing in all of the camber information and the stud information. It tells me warning here. This is just showing that some of the bracing connections changed, which I'll show you what that means shortly here as well. So this, it brought in all the loads. We'll process it here. And actually, I should have did this last. After I bring in the loads, then I set the vertical brace points to half nominal depth supporting beam. Do that again real quickly here. So that's in, and let's just click on one of the members here. And as you can see, the loads were imported. So now instead of auto being checked for the loads, actual loads are brought in. The loads are fairly small. And then we'll go to our isometric view here. We'll process the job, create solids. It designs all of the connections in one click of a button. And then we'll look at everything in solid view. We have these slabs here, so what I'm going to do to just make it easier to look at is turn off that part of it in the display options. So we have all our connections created here. And as far as connection design, I'm going to show off some of the important things. One is connection calculations. And if to look at the connection calculations, you go to reports and then down to connection design calculations, which gives you the short version, which is just 2 or 3 pages per connection, or the expanded calculations, which I'll show you, and either you can do it for the whole job or you can pick members that you want the calculations for, and we'll just do it by location, and we'll pick one of these members here. It'll take just a second to create the connection calculations. And we'll scroll down here. This is the calculations. They start out by just showing some of the general information about each of the about the connection, and then about halfway down on the first page, they show all of the specifics regarding the connection, regarding things like the gusset plate thickness, angle sizes, weld sizes, and so bolt sizes, number of rows of bolts, and so forth. Some people, when they're creating the calculations, will maybe put a screenshot of the connection right here if they're submitting that to the fabricator. And then down here, it gives the summary of the connection design, showing all of the different limit states that were checked, the capacity for each of the limit states, and then the AISC reference of where that limit state calculation came from. And then the short version of the calculations stop right here. So if you only want the short version, you're only going to get like 2 or 3 pages per calculation. And this is a nice summary table. But then if you want to get into more detail, you can scroll down and look at the detailed calculations for each limit state, showing all of the different values that are entered, all the different variables, the formulas, the numbers plugged into the formulas, and then the final calculation for each of the different limit state checks. So as you can see, the calculations are very detailed. A couple other things I'll show you in the connection design criteria window. We're designing in this job to the LRFD 14th edition manual. As you can see, we have all of the current and recent AISC codes. I just spoke with our chief engineer. The work for the AISC 15th edition manual is all done with the software, and it'll probably be in the next version. We have several different Canadian codes that you can design to, an Australian code, and a couple different Euro codes, and then we recently added the Euro code as well. I showed you before we imported the loads from SCIA, the loads were set to auto, and if auto is set, it goes to this table here, and you can either design for a percentage of the uniform allowable load or a percentage of the maximum web shear for beams. Same with moment connections. You can design for a percentage of the moment capacity of the beam, or same with bracing. You can design for a percentage of the tension or compression capacity of the braces. And one person asked me recently, would it be possible to design for either the maximum, or would it be possible to design for the maximum of the SCIA imported load and the auto load that is calculated within SDS2? And I talked to a programmer about that, and they said they could write a parametric for that, and that would be fairly simple and straightforward. It'd be two parametrics. The first one bringing in the SCIA loads, and then the second one calculating the auto loads and comparing it to the SCIA loads, and then replacing it if it's greater. So that is possible. Down here, the uniform force method. It designs the bracing connections per the uniform force method, and you can either assign no special case. Special case 1 is moving the work point, and I'm going to show you an example of that here fairly shortly. Special case 2 is where you take the vertical component that's going from the gusset to the beam and applying that and transferring that to the column instead, and creating some moment at the gusset to beam interface. And it used to be that it was set up to put all of the, it's called the delta V sub B, all of delta V sub B into the gusset to column connection. Now we, in a somewhat recent version, we added the capability to dictate how much of the delta V sub B that you put in the gusset to column connection. And then special case 3 is just when you're connecting only to the beam and not to the column at all. Also, we can do a seismic vertical brace gusset design, and we have the option for SCBF or OCBF. A little bit else, a couple other things I want to show you. Auto standard connections. As I said in the beginning slides, you tell it what type of connection you want in what situations, and you have, every connection configuration and type that you can think of. And let's say the most common one is the beam-to-beam connections, and even more common is the wide flange beam to wide flange beam into the web perpendicular. Right now it's a clip angle connection, but if you want that set as something else, you just double click on it. You can change it to anything else, maybe an end plate or a shear tab, and then you can change some of the specifics of the connection itself. And this is the connection it would automatically design for beam to beam wide flange connections that are orthogonal. So this is easily changeable, and then you can override this per connection as well. Getting back to the model here. Changing the work point. Let's look at this brace here. Where is that? We're navigating between views is pretty easy as well. You just double click on a column row to go to a certain column row. But as you can see, this brace right here, the gusset plate is somewhat large. So if you want to change, if you want to go with special case 1 of the uniform force method, you change the work point from the intersection beam and column to the point at the bottom of the column and the face of the beam here. So you do this by changing this to a stick view at first, so it's just a line, and then you can add construction lines in on the members themselves to make it easy to grab. And then you grab the end of the brace and you select move stretch members, and then you go from the end of the brace here to, let's go the face of the beam, bottom of the column, and then you right click to confirm the move. And as you can see, it redesigns the connection with a much smaller gusset plate with the work point moved. Also, you can lock some variables in. I told you that the connections are fully customizable, so if you double click on the connection itself, you see a picture of the connection, and you can change any of these variables to anything you want, as long as it works for the loads. And we'll try to change a couple of things. So we could change the number of rows of bolts to, let's say, 3 for the claw angles. Change the number of rows of bolts to 3 for the web plate. And also, let's change the plate thickness. Right now it's a 3/8. We can go to 1/2. One other thing I want to show you, pay attention to these values over here. These are automatically adjusted as you change things in this window. So I changed the plate thickness to 1/2. As soon as I hit the tab button, let's say the gusset block shear will change. Right now that's at 257.2. And as soon as I hit tab, it jumps up to 343 kips. So this is a good thing to do if you want to modify a connection. You can see what limit state's controlling and adjust things on the fly here. So we change these values, and then the connection automatically changes. And if you want to save that connection, you certainly can. You double click on it again, and then you click this thing that looks like the Hubert icon here, and you can name the connection. And every company has their own naming configuration for connection, and you can name it something really short or really long. It can be as long as you want. So I'm going to name this like VB R equals 3, T equals 1/2. So I know exactly what it is. And then if I want to apply that same connection anywhere else, I can select one spot or many spots, and I just change the connection type to user-defined, and then I open this file cabinet here. Now, most of our customers have dozens and dozens, maybe even hundreds of different user-defined connections in their library, and you can create anything you want. So in a real job, you'd probably have hundreds to choose from here, and you'd pick one. Since this is a brand new job, I only have one here, so I'll double click on it, hit OK, and then this connection automatically changes to that user-defined connection. Let's see, let's go a quick example of a constructability check. We'll go to elevation 15.0, and this is one I like to show. Let's cut out the top flange of the beam here so you can see what's going on. Change our depth check here. So we're looking at the top flange of the beam. We can grab this beam and move it over from, let's say, this point here, and we'll move it, let's say, 2 inches in the Y direction here. And that moves over. As soon as I confirm the move, it redesigns the connection and makes this work, and it changes these angle sizes to something that works so the beams on opposite sides of this beam can share the bolts. One other thing I wanted to show you, I told you that SDS2 engineering does have some analysis capabilities. So you're going to do most of the hardcore analysis within SCIA, but then once the job is brought into SDS2, if you happen to change a beam size or move some beams around and you want to reanalyze the floor, you can easily do that. Also, as part of our eRector Plus station, you have the ability to analyze a partial frame. Let's say this is a huge job, and as an erector, you want to just look at a portion of the structure and analyze it to see if you might need cable bracing. We can do that. Let's look at elevation, the top of steel elevation at the top. And let's say you only want to analyze part of the structure. What you can do is you can just grab the part of the structure you want to analyze, go up here and say create partial job, It automatically, you can name it anything you want. And then you can open up the new job. You go into the modeling screen, this partial job that you created, that's just a portion of the structure that you brought in. And here's just that partial job. Then you can node number in order to create your analytical model. And you could apply global restraints and all of that. We won't do that right now. So you do the node numbering. And then if you want to, let's say, apply some wind loads, you can go here to model wind load add. And you can adjust these values however you want, and there's other things that you can put in the setup criteria. Let's say this is the north face, and then you can look at the wind loads on the north face, and you go back to the isometric view, and you have the wind loads applied on the individual members, and then you can analyze it and see if you need to put in any cable bracing for erection purposes. So that's one way that you can use the analysis capabilities of SDS2 engineering. I see that it's 12 minutes before the hour, so I'll probably take it back to Ben so he can finish up and we can get to questions. So how do I give you back the screen, Ben? Or can you just take it back from me?
Okay, thanks, Steve. Yeah, just a little recap before we get into questions. Really, with this workflow between SDS2 and SCIA Engineer, in SCIA, really we're focusing on the full modeling and analysis of steel structures, really any steel structures, and so a lot of the modeling capabilities allow for a lot of flexibility in what you can create. Obviously, again, the design of steel and composite steel structures according to AISC 360. Stephen mentioned some other codes. SCIA also includes other codes like full support for the Euro codes and other international codes, Brazilian codes. And so, today we've been focusing on the American codes in this particular webinar. Obviously, we showed a lot of those detailed outputs for the design checks. And then finally, the export of geometry and loads and other member data information via IFC and XML. For SDS2, Steve really went through that comprehensive connection design, not verification, of those connections according to the AISC codes, but also Euro codes, Canadian codes, Australian codes. There's other standards that exist in SDS2. Those are really nice constructability checks, not just, hey, does my connection work, but hey, does it actually fit? Can it actually be built the way that I'm saying it can, so you don't run into any of those issues later on down the road in CA phase. Fully customizable connections and complete detailed calculation reports, really allowing you to be as flexible as possible with how you model and how you build those connections or how you build your standard connections, and then being able to document them as much as possible. And so all of this really gives us a really great workflow for taking the information that we maybe get from an architect or a designer into structural engineering, and then finally into the rest of structural engineering for connections and fabrication. And so at this time, you have the questions window. And so if you'd like to ask any questions at this point, Steve and I will have some time to answer some questions. So in the questions window, you can just enter your questions, and we'll be happy to answer whatever we can over the next kind of 10 minutes. So someone had asked some questions about different loading conditions, particularly in SCIA Engineer, asked about different kind of uplift loading. I know there's other softwares that don't support uplift loading. So SCIA does support uplift. If you're using SCIA's three-dimensional wind load generator, it will also automatically create uplift loads for that. As far as unbraced lengths, SCIA will always use the unbraced length for a controlling condition, and so it's cutting the beam at sections. So if the moment or if the loads at a certain section are being controlled by the uplift pressure, the unbraced length will be reflective of that, obviously. And so it can essentially change to give you the worst case unity check on a particular member. Someone asked just about some flexibility and being able to kind of set the standards of SCIA Engineer, whether it's the units or the way things look. So everything in SCIA is kind of customizable. If you want to get rid of certain buttons or tables or palettes or whatever, you can kind of dock them and undock them. You can set up the different units in certain ways. It's really up to you, so there's a lot of flexibility there. Someone asked about the CSA code in SCIA Engineer. So it's something we're talking about, looking at adding the Canadian Steel code in SCIA Engineer, probably something that we would look to do in the next release or two. I think it's something that we would anticipate kind of coming sometime next year. Can you create composite members with SCIA, or is it only for shapes? So we can create composite members. So I'm not exactly sure what types you're looking for, but in SCIA we do have something called the General Cross-Section Editor, where I can create a member, or really we can just draw or create or input any types of shapes. Now there are some standard libraries that already exist. So if we look here, there are some standard welded and sheet welded built up members that already exist by default in SCIA, but if you need something even more complex, even more general than these types of either welded or sheet welded shapes, we can go ahead and use what's called the General Cross-Section Editor and import a DWG file or really build whatever you want. So Steve, I guess there was a question about what if you had existing connections that you wanted to model in a building? Kind of how would you deal with that in SDS2?
Oh yeah, excellent question. What you would do is you'd create a user connection, and you would take all of the measurements off of that existing connection and input that as a user connection exactly as it is in the field, and then get the capacity from that. So you can certainly put in existing connections.
Cool. Thanks. Somebody asked about the column splice, and so in this particular case we did model a column splice. So there's a few different workflows for how, if you want to include column splices. Typically in structural analysis software we don't model our columns in this fashion. You would either model them kind of full height in this particular building, or you would model them from floor to floor, level to level, depending on what software you're familiar with. In SCIA, there's a variety of different options. We could have modeled them from level to level and then sent the model to SDS2, and then in SDS2 that those locations could have been changed to add those splices. You could also do what we've done here in this case and really truly model the first floor column basically up to maybe this point that's 3.5 feet above the floor, and then send this information. And this information, the joint here, the node at that location, as well as the axial forces there, will come into SDS2 and we'll design that splice connection. So it's really just a matter of how you choose to deal with it, and really that's, I think, all about a conversation with your detailer, your fabricator, your connection designer who's using SDS2. What's the best way? How do you want to communicate that information? Let's see. Do we have any other questions? We did have a question. I guess this is both. We can answer. Each of us can answer this question. It's both for both of us. Tryouts of the software. So for SCIA, you can go to our website www.scia.net, and right there's a button for a free tryout. You can get a free 30-day tryout of the software. It's a full version of the software. And there's really no limitations other than a watermark on the documentation, because obviously we don't want you to produce jobs with that. But you can just apply and have a 30-day trial of the software. For SDS2, Steve?
Yes, same thing with that. You can't actually download a free trial, because in order to run the software you need a USB hash that I would need to send to you. So I would just start out by, if you're interested, get in touch with me. I'll start out by just showing you a demonstration, answering all your questions. And if I'm still pretty sure, if we're still pretty sure that you want the software, that it'll meet your needs, then yeah, then I'll set you up with a trial, and then you can more than likely purchase it. And then we have leasing options on the software as well, with which I can tell you in detail about it, and I'll make sure you have our contact information before we finish up here, so you can get in touch with me, or I can get in touch with you for a more detailed demonstration. I didn't cover a fraction of what the software does in today's demonstration.
So Steve, there was another question. Does SDS2 allow for the generalized uniform force method per Appendix A of AISC Design Guide 29?
I am not, Appendix A of AISC Design Guide 29. I don't have it on my shelf. I'm sure it does. I don't know the answer off the top of my head, but the traditional uniform force method, where there's some vertical component going into the beam, some vertical component going into the column, and same with the horizontal component. It does that. It's, uniform force methods, no special case, but I would have to look at Appendix A of Design Guide 29 to tell you for sure, so I'll get back to you on that question.
Okay, perfect. There was a question about what information do you input for diaphragms, metal decking, elevated slabs. That's obviously for SCIA, I think. In this particular case, whatever you model, so you can pick to model a deck. You actually choose the Volcraft or Can-Am or Verco deck or composite deck. That deck can also be chosen to be if I select here, you can see that this particular composite deck is a rigid diaphragm. There's obviously standard finite element, flexible, rigid, or semi-rigid diaphragm actions. Obviously, by default, this metal deck here is a flexible diaphragm, so all of those options exist as you do the analysis of your particular project in SCIA Engineer. So let's see, are there any last-minute questions coming in? I think it seems that that's about it. So I think this is probably a good place to stop. Obviously, if you have other questions, we can certainly get in contact with you. We have everybody's contact information. If you have other questions, both Steve and I's email addresses are at the bottom of the screen right here. So any SCIA-related questions, you can certainly contact me, or any SDS2-related questions, please contact Steve. We will be sending out certificates of attendance over the next few days. It'll just take us a few days to kind of process everything, get everybody's information into the system, and then create the certificates and send those emails out. So you will get those from us in the next few days. And then if you have any other questions, by all means, let us know. You'll also be receiving an email tomorrow with the link to viewing the video of this particular webinar. And finally, the webinar will be uploaded to the SCIA YouTube page, and I'm guessing we could also post it on the SDS2 YouTube page in the next day or so. So just go on to YouTube and search either SDS2 Design Data or SCIA Engineer, and you'll be able to find the webinar recording. So with that, I appreciate your time, and Steve and I appreciate your attentiveness and your questions. If you have any questions, please let us know. Otherwise, we thank you for your attendance, and we look forward to talking to you more about SCIA Engineer and SDS2 in the future. Thanks very much. Have a great day.